Warning: lithium is a very reactive metal and may burn or explode on contact with water or air. Hi guys, here is MIH. 5 months ago, I posted a video about making lithium metal by the electrolysis of molten lithium chloride and potassium chloride. While it worked, the yields were extremely low. More recently, I uploaded a theoretical video where I reviewed the main methods of making sodium metal and came up with the conclusion that the propylene carbonate electrolysis route seems the most viable. So I decided to try this method out for lithium production as a test before I actually go into making sodium. For this preparation, you'll need some propylene carbonate, some lithium chloride, and a little bit of paraffin oil. The exact quantities are not critical and simply depends on the reaction scale you choose. Because this is a test run, I only used 30 milliliters of my valuable PC. To start, take around 0.1 grams of lithium chloride and dry it over a hot plate. This is very important since the reaction system must be free of water. When no more water vapor is given off, the beaker is removed from heat and allowed to cool a bit. Then around 30 milliliters of propylene carbonate is poured into the beaker. You can see that PC is a colorless liquid that resembles water. The beaker is placed on the hot plate again, and around 5 milliliters of paraffin oil is poured on top of the PC, which isolates it from atmospheric moisture and oxygen. Lithium chloride is only sparingly soluble in PC, and heating it up helps improve the dissolution. When the beaker starts to release fumes, it is removed from heat. Next, an aluminum foil anode and a copper sheet cathode are placed into the solution. The copper can be replaced with any common metal, but the aluminum cannot be replaced with inert anodes such as graphite, and I'll explain why in a moment. The alligator clips are connected and the 12-volt power supply switched on. You can see that the copper cathode immediately darkens and some bubbles are released. Anyways, what is happening here? The lithium chloride first dissolves into the PC and dissociates, forming lithium ions and chloride ions, just as it does in water. Because there are very few hydrogen ions in the PC solution, the lithium ions can gain electrons and plate out on the cathode as a thin layer of lithium metal, which is the tarnish you see on the copper. The anode is generating chlorine, which immediately reacts with the aluminum to generate aluminum chloride, so only a few bubbles can be seen. After a few minutes, I took the copper cathode out and immersed it in some water. Immediately, the thin layer of lithium reacted with the water to release hydrogen. Therefore, look, the experiment is successful. At least it actually gives lithium. The main problem with this production method is that the lithium chloride has very poor solubility in PC, in fact only a few grams per liter, and so the current running through is very small and the electrolysis speed very slow. There are two methods to increase the reaction rate. You can skip this 2-minute long explanation and directly jump to the takeaway version. The first method is the in situ generation of aluminum chloride. The aluminum anode we use can react with the chlorine produced in the electrolysis to form aluminum chloride, which then reacts with the extra lithium chloride present to form a complex that has a much larger solubility. Also, since the chlorine is always generated no matter what the electrolyte is, the aluminum anode can produce more aluminum chloride along the way, making the reaction go faster and faster over time. Obviously, if you have anhydrous aluminum chloride, you can add it prior to the reaction and produce lithium fast from the start. However, anhydrous aluminum chloride isn't easy to get for everyone, and it is rather difficult to handle, so I came up with this in situ generation method instead. Still, because of the very limited solubility of lithium chloride in PC, the reaction is still going to go very slowly at first, until enough aluminum chloride is generated and the speed picks up. This problem is solved by connecting a very high voltage power supply, such as a few 9-volt batteries, to the cell. This will increase the current by a few times and allows you to quickly produce aluminum chloride and make the slow production period shorter. Alright, here's the takeaway. If you have anhydrous aluminum chloride, then add it into the PC along with the lithium chloride prior to the electrolysis. You can skip the slow production period and produce large quantities of lithium immediately. If you don't have anhydrous aluminum chloride, follow the video's procedures. The reaction rate starts very slow but gradually increases over time. To shorten the slow production period, use a higher voltage power supply. Note that this in situ aluminum chloride generation method doesn't work with sodium production, because the sodium chloride is practically insoluble in PC and cannot conduct even a little bit of electricity to get the reaction started. If you don't have anhydrous aluminum chloride and still wanted to make sodium by this method, you can start with a kickstart lithium cell, wait until it produces lithium at a fast rate, and then switch out the lithium chloride input for sodium chloride. The sodium metal product will be contaminated with a little bit of lithium, but that doesn't impact most uses. Anyways, the electrolysis continued uneventfully. I tried to measure the current, but it was so small that my ammeter cannot detect it. There may be occasional bubbles forming on the electrodes, but apart from that, the only thing changing is the color of the copper cathode, which gradually turned completely covered by a gray layer of lithium. Around 9 hours into the electrolysis, the aluminum anode is visibly corroded, which is a very good sign that something is happening. You can see that the part of the foil close to the cathode is eaten away, and the edge of the foil turned black due to exposed aluminum particles. From this point on, the cell is pretty much on autopilot. I let the cell run on its own for a week and came back to check it on the weekend. Some lithium chloride has crystallized on the cathode, which wasn't expected. The amount of lithium deposited apparently stayed the same, but the aluminum anode was severely corroded, which tells me that the cell is at least still going. When the electrodes were taken out, the electrolyte appeared slightly yellow, and some black stuff gathered at the bottom. I added some electrolyte in water to see if it will have a vigorous reaction, but nothing apparently happened, which means there is not much aluminum chloride inside it. This makes me feel sort of worried that the cell is taking way too much time to catch up its supposed to be fast speed. Anyways, I then replenished the cell with some more lithium chloride. I dried some of the salt on a hot plate, pulverized it, and added it to the electrolyte solution while it was heated. I found that heating the PC really helps increasing the solubility of lithium chloride in it and greatly speeds up the initial rate of electrolysis. When I came back to the lithium I produced, it has reacted with the air to form a yellowish layer of oxides. I put it in some water and it produced some large bubbles. From this point on, I'll stop testing things around and throwing lithium in water and actually collect my lithium metal produced. I cleaned my copper cathode and weighed it. The cathode weighed 0.5 grams, and after this run, I'll weigh it again to find how much lithium I produced. I connected the power supply and restarted the electrolysis. 2 days later, a decent amount of lithium deposited on the cathode. I took the cathode out and weighed it. Its mass turns out to be 0.76 grams, which means that around 0.2 grams of lithium was made in the run. I then did my best to scrape off the lithium using a spatula, and this is our yield of lithium metal from roughly 45 hours of electrolysis. It doesn't look like a lot, and it sure wasn't a lot, but this lithium is truly made at room temperature and without any really expensive or exotic reagents. Also, around 1 hour after I harvested, the cell was blown down by the raging wind and my raging curtain, and I lost nearly all of my precious electrolyte. This made the 0.2 grams of lithium even more precious to me. Anyways, this project was a fantastic success, at least on a proof of concept level. The next step is to improve the electrolysis speed and the collection method, which I'll do very soon. Thank you for watching.